Hey there, it's Shannon Math Chick Myers, and today we'll be looking at section 14.6 in the Larson and Edwards calculus text, which covers triple integrals and applications. So our goals today are to use a triple integral to find the volume of a solid region and to find the center of mass and moments of inertia of a solid region. So let's go ahead and warm it up by setting up a double integral to find the volume of the solid bounded by the graphs of the equation. Z is 1 over 1 plus y squared, x is 0, x is 2, and y is greater than or equal to 0. Good, good? Okay, so here we go. If we just kind of take a look at our picture, we'd have something along these lines. Oops. All right, so x is bound between x is 0, the lines x is 0 and x is 2. So we'll have, let's see, and then y is bound at 0, but we haven't been given an upper bound, right? So and then this one here is y is 0. So we've got, this lower bound for the region, but we're going to have to utilize an improper integral in order to complete the problem. We'll just give a kind of a picture of part of our region, right? So now, setting up our integral, we would have the volume is equal to, so we know that x is bound between 0 and 2. Y is an improper, but it's bound at 0 to up to infinity. So, and then we have this 1 over 1 plus y squared, and we'll go for dy dx. Cool, cool? Okay, so our volume will be the integral from 0 to 2. This is an arctangent result. I'm not sure if you remember, but we'll actually go ahead and we'll show all the steps. So the limit is b approaches infinity of the integral from 0 to b of 1 over 1 plus y squared dy. So we're going to be focusing on this guy here, dx. So then our volume will be the integral from 0 to 2. The limit as b approaches infinity of arc tangent y evaluated from y is 0 to y is b. And again, after we do this one, we'll be doing the next integral with respect to x. So this will be integral from 0 to 2 of the limit as b approaches infinity of arctangent at b minus the limit as b approaches infinity of arctangent at 0. And then we'll still be integrating with respect to x. So the second, well, I'll talk about that one in a moment. So we'll be going from 0 to 2. If you recall, the arctangent function has a horizontal asymptote at pi over 2. So we will end up getting pi over 2 for that limit. And arctangent at 0 is 0. And the limit as b approaches infinity of 0 is 0. So we'll just have real easy integral now, integrating pi over 2 with respect to x. So that's going to be pi over 2 times x, where x is tending from 0 to 2, or going from 0 to 2. And so this will give us, at the end of the day, pi cubic units. How'd that go, okay? Awesome. All right, so definition, triple integral. So if f is continuous over a bounded solid region Q, then the triple integral of f over Q is defined as, got this triple integral, which is Q right here, and then you're going to have f of x, y, and z dv, which ends up being the limit as the norm of delta approaches 0, and that will be of the summation from I equals 1 to n of f at xi, yi, zi, and then delta vi, provided the limit exists. The volume of the solid region Q is given by, we'll have volume of Q the triple integral of Q dv, or triple integral over the region Q with respect to v. All right, so let's take a look. Evaluation by iterated integrals. So if we let f be continuous on a solid region Q defined by, so x is between a and b inclusive, y is between h1 at x and h2 at x inclusive, and z is between g1 at x and y and g2 at x and y inclusive, where h1, h2, g1, and g2 are continuous functions. If that is the case, then this triple integral over the region Q of f at x, y, and z with respect to v is equal to the integral from a to b, that one's going to relate to the x, the integral from h1 at x to h2 at x, that's going to be relate to the dy, and the most inside one will be the function of x and y. So g1 at x and y to g2 at x and y. And then we'll have dz, dy, dx. But you're going to find out that you don't have to do it in that order. So we'll just keep carousing along and see how it goes. All right, so let's evaluate the iterated integral. We'll just start out easy here. So here we go. We've got the integral from 1 to 4, the integral from 1 to e squared, and the integral from 0 to 1 over xz of natural log at z with respect to y, so dy, dz, and then dx. So here we go. Our very first one that we're going to deal with is this one here. Okay. All right, so we will get the integral from 1 to 4 the integral from 1 to e squared. And then we'll be treating natural log at z as a constant. And then we'll have y, where y is evaluated from 0 to 1 over xz. Cool, cool? And then we will still have dz dx. So this is what we've got so far for the equivalent. All right, so now this will be the integral from 1 to 4, integral from 1 to e squared, natural log at z, and then when I do the lower limit of integration, it will zero out. So I just need to multiply by 1 over x times z, dz dx. Cool so far? Okay, now here we go. I'm gonna go ahead and separate out what's treated as a constant just to make this one easier. So we'll be evaluating the integral from 1 to 4. In this case, 1 over x is going to be a constant because we're going to be integrating with respect to z. So we'll be integrating from 1 to e squared of natural log at z over z with respect to z. And then we'll still have our dx that we'll need to take care of. So here's our second one that we're dealing with. Okay, so this is going to be the integral from 1 to 4. And we have our 1 over x being treated as a constant. And this will end up being what? Well, if we have natural log at z, that whole quantity to the 1 power, our g of z is natural log at z, and g prime at z would be 1 over z. So that means we will have natural log at z, the quantity squared. That's going to be evaluated from z equals 1 to z equals e squared. Continuing, we will have the integral from 1 to 4, and then 1 over x is still hanging out. And then we will have natural log at e squared squared minus natural log at 1, that whole quantity squared. And we'll still have our dx hanging out. So this is the continuation of working the green integral. And almost there, hang on. So 1 to 4, integral from 1 to 4, we have 1 over x. Natural log at e squared is just 2 because you're evaluating the natural log at the natural exponential. So whatever's in the power of that exponential is what you get. And so then we'd be squaring 2, and then we would be subtracting 0 squared. So it ends up like this. So we'll end up with the integral from 1 to 4 of 2 times x to the negative 1 with respect to x. And so that's going to be 2 times, good, natural log at absolute x, and that's going from x equals 1 to x equals 4. So, and by the way, this is our last integral that we're dealing with. And we'll have 2 times natural log at 4 minus natural log at 1. Remember, natural log at 1 is 0. And then, so we'll just end up with 2 natural log at 4, which gives us what? Awesome. Natural log at 4 squared, which is natural log at 16. Cool, cool? All right, so next up, let's set up a triple integral for the volume of this solid. So the solid that is the common interior below the sphere, x squared plus y squared plus z squared is 80, and above the paraboloid, 1/2 times x squared plus y squared, that quantity. So to graph the sphere, you got to do z is plus or minus the square root of 80 minus x squared minus y squared. And then now let's add another deal to the graph. And it's that paraboloid. So this one will be, oh nice, it's almost started for us. We have an x squared plus y squared. And then we want 0.5 times that. Awesome. So, do you see the little, it almost looks like a little hat here. Okay. All right, and this one. Cool. Gosh, I love technology. Isn't technology awesome? All right, so we've got a good visual here. Here we are. We're back. So remember it said the common interior that's below the sphere, and then and above the paraboloid. So we're looking, if this one, let's look at this. So I'm going to just sort of trace the outside, the sphere right here, so we can see there. And so the volume that we want was below the sphere, and it was above the paraboloid. That was the common interior. So I'm thinking it would look something like this. So let's see what's happening with these things, all right? So z, okay, is going to go between the sphere, which if you isolate z, it's the upper half of the sphere. So it would be, let me move it over a little. It would be z equals the square root of 80 minus x squared minus y squared. Cool, cool? And that's this part of it. I'll just kind of dash it in. Now, the bottom part of z, so that would be like our g2 of x and y equals that. Now our g1 of x and y is going to be the equation for the paraboloid, right? So as we are going, we would have I do it the other way. We would have g2 of x and y would equal to, whoops, not c2. g1 of x and y, that's g2 of x and y. And this we could call, I guess, z2. We can call this z1, if you will. Actually, let's just take the z's out of there. I think that's a lot less confusing. Okay. So our g1 of x and y is just the 1/2 times x squared plus y squared. Cool, cool? All right. Now, so that's going to be our business for the dz part. So let's get that one set up, and we'll go from there. So the start of our volume is equal to, we're going to do the dx last, so I'll just leave some space. We're going to work from the inside out, all right? And then we figured out our g1 and g2 of x and y. So our g1 of x and y was 1/2, do it in the same colors I did the figuring. So 1/2 times quantity x squared plus y squared. And then the top was the square root of 80. I never leave enough space, I'm sorry. All right. The square root of 80 minus x squared minus y squared, because that's the top of the sphere. Now we need to figure out, and so that is this part was the dz portion. So this, all the pink is what we just figured out. So now let's focus on the y. So for y, we'll do y in purple. All right. Let's think about this. We've got that z is equal to 1/2 times quantity x squared plus y squared. And so that gives us that 2z is equal to x squared plus y squared if I just multiply both sides by 2. Cool so far? Awesome. Now, we also know that x squared plus y squared plus z squared is 80. And that's from our sphere. So, using this fact that 2z is x squared plus y squared, we can substitute in and say 2z plus z squared is equal to 80, right? And remember, because 2z is x squared plus y squared. And so factoring out a z, we would get, nope, sorry, not factoring. So we would end up with, I'm going to add a page here. So we would end up with z squared plus 2z minus 80 is equal to 0. And then solving for z, right? Let's see what happens. So 8 times 10, right? Positive 10 times negative 8 as they combine to be positive 2 and have a product of negative 80. So we would have z plus 10 times z minus 8 is 0. So z would either be negative 10 or z would be 8. Well, since z is equal to 1/2 times the sum of two squares, it has to be positive, right? Z has to be greater than or equal to 0, okay? Because we're going above that paraboloid. So this one we won't use, and we'll get z is equal to 8. So this is what we will utilize. Okay, well, we know that coming back to this equation here, 2z is equal to x squared plus y squared. That'll give us 2 times 8 is x squared plus y squared. Right? So we will get x squared plus y squared is 16, which is 4 squared. So you basically have a circle with radius 4 in the xy plane where we connect with z here. Okay? So, ready? So basically, now, if we've got a circle and we want to isolate y, right? Y would be plus or minus the square root of 16 minus x squared. So, h1 of x would be the lower, or the negative root, 16 minus x squared, and h2 at x would be the upper half of this circle, so you'd have, or the positive root, 16 minus x squared. Cool so far? All right, so we would have, in the purple, for our y dy stuff, we're going to have negative root 16 minus x squared, and then positive root 16 minus x squared. And x, since we're dealing with a circle, is just going to go from beautiful negative 4 to 4, because that's the radius of our circle. Awesome. And so we've got this setup here, and it's all done. So this is how we would set it up. And honestly, it would probably be much easier in polar coordinates, don't you think? Or no, actually, we'd have to use not polar, but we'd have to use we'll be covering that in the next section. It'll be utilizing cylindrical or spherical. All right, so there we go. And then just again a visual. So here, right here, this would have been the circle we would have been looking at for that. That would be our circle. X squared plus y squared is 4 squared. Okay. All right. Awesome. So technology sure helps one visualize this stuff. All right. So now let's look at our next example. Sketch the solid whose volume is given by the iterated integral and rewrite the integral using the indicated order of integration. So here we go. I made a grid for us. And so we've got, let's see, our z is going from 0 to the square root of y squared minus 4x squared. So let's work with that, okay, first. So, because in order to get a feel for this, we're going to really want probably to make a picture of what the heck is going on here. Here's all the information we have, okay? So 0 is less than or equal to x is less than or equal to 2. X is less than or equal to y, which in turn is less than or equal to 4. And 0 is less than or equal to z, which in turn is less than or equal to the square root of y squared minus 4x squared. Cool so far? So just as an identifier, the way these are right now in our, our rule for the triple integrals, okay, is this right here is our A, the 0 is our A, and the 2 is our B. Cool so far? The 2x is our h1 of x, and the 4 is our h2 at x. And then, I'll go above this time, the 0 is our g1 at x and y, and then the other one, the root y squared minus 4x squared, is our g2 at x and y. Cool so far? Now we are being asked to not only sketch the solid, but we want to rewrite the order where dx and dz are switched, right? And so what we need to find out is x is going to have to be written in terms of y and z. Does that make sense? And then y would be written in terms of z, and then z would have the constants around it. Cool so far? So that's kind of the evil plan here of what we need to figure out. So let's do it. Let's go ahead and let us figure out what's going to happen with all this cool stuff. All right? So z has that lower limit of 0, right? So we're okay there. So we're the x y plane is going to be our lower, our floor, if you will. And so z is 0. Now we need to find a constant for z, right? So we also know that z is equal to the square root of y squared minus 4x squared. Good so far? So if we let x equal to 0, then z is equal to, good, the square root of y squared, which would be plus or minus y. But remember that that z has to be positive, and y is between 2x and 4, and x is between 0 and 2. So we're going to have all positives here. So z is y. When x is 0, z is y. Cool so far? Now, what about when x is 2? When x is 2, because we've got that middle integral. So if we consider y is 2x, we know that from the lower limit for y. So when x is 2, right? Or actually, let's say at x is 0, y is 0. And so do you see that means that z is 0 too, because z equals y. So we're going to have an ordered triple at 0, 0, 0. At x is 2, okay, y is going to be equal to 2 times 2, which is 4, which will equal to z. So we'll have another ordered triple at, 2, 4, and 4. Good so far? All right. So let's see what else we need to think about. We also know that y is 4, right? So I'll write it right here, and y is 4. So now let's take a look at, we want to write x in terms of y and z. So utilizing this one here, all right, this means that z squared is y squared minus 4x squared. Isolating x with a little algebra, we're going to have the positive root of y squared minus z squared over 2, right? So I just isolated x and noting that x is positive. Okay, so here we go. I think we have, enough information to do our thing here. So we have y equals 2x. And remember, we found a couple ordered triples as well, right? And so we also know that z equals 0. We've got a floor there. So we know we're going to have an ordered pair at 0, 0, 0, right? And at 0, 0, 0. We're also going to have an ordered pair at when we have y is 2x, right? So when x is 2, y is going to be 4, right? So we'll have 2, 4, 0 as another point. So now let's figure that out. So I think it'll be about here. And so this should be the line y equals 2x. Cool so far? You're also going to have this line, y is equal to 4. So it's going to be going like this. So y is equal to 4. Cool so far? So that's going to take care of the x, y plane. For the most part, we need to do our x is 0. So if we do our x is 0 all the time, right, it's going to look something like this. So this would be when x is 0 and z is 0, remember, so y would be 4. All right, and then so now we've got the kind of floor of it. And so now let's look in terms of y and z. Remember, we had found out that z equals y, right? So when y is 4, z is 4. And so if we would end up with, in the yz plane, we would end up, we already know we have a point at 0, 0, 0, right? And we're going to end up with 0, we'll end up with 0, 4, 4 as well. So that one I'll do in, I don't know, something bright. So 0, 4, 4. So something like this. So we're going to have this right here. And everything, you know, will actually, let me do it in this color here. Looks too much like the other one. And so that gives us y equals z, which of course is the same as z equals y. And then we have our other information, right? Because we know that y is 4, so z has a value at 4 as well. And so that's going to close us off here. And so the picture of it, you know, will look like this. So that'll be our solid of interest. Cool, cool. All right. So now let's just identify what our new limits of integration are going to be. So we know that z is going from 0 to 4. Let me block this stuff off. And so our middle one, right, needs to be a function that's in terms of y, right? Our middle function needs to be y equals some function of z. So remember, we have that line y equals z, and then it goes up to y equals 4. Cool, cool? And for the x one, the more complicated one, and x in terms of the both variables, we are going to have x going from 0 to the square root of y squared minus, y squared minus z squared over 2. And that was from the work over here. Cool, cool? All right, and then that's going to be dx, dy, dz. And that's what we were asked to do. All right, so I don't think that we needed to evaluate it, so we'll just leave it. All right, so now, fun. List the 6 possible orders of integration for the triple integral over the solid region. So here we go. X is between 0 and 2. y is between x squared and 4, and z is between 0 and 6. So again, all of them are going to be positive. So the easiest one is going to be this integral here that's shown, right? 0 to 2, x squared to 4, and then 0 to 6. So our f of x, our f of x, y, and z is our x times y times z, and we've got dz, dy, dx squared is less than or equal to y, which in turn is less than or equal to 4. Looking at this piece of it, x, if we look at x squared equal to y, x would equal to plus or minus root y, but we know they're all positive, so x would be root y. Okay, so let's check it out. Another way we could integrate is if we take a look at keeping the dz here, but switching the dx and the dy, then we will have y ranging from 0 to 4, because when x is 0, y is 0, right? And then here we would have what? Beautiful. 0 to root y, and then 0 to 6. And then we still have our f of x, y, and z is x times y times z. Cool, cool? Okay, so now let's take a look at, I don't know, we can go ahead and start having dy in the most inside. So just make my integrals here. X, y, z, x times y times z. So let's say we did, I don't know, dy, dz, dx. So if we do dy, dz, dx, we're going from x squared to 4, right? And then, 0 to 6, and 0 to 2. All right, another way, let's keep the dy on the most inside and switch the dz and dx. So we'll have dy, dx, dz. All right, so we'll be going from x squared to 4 for our y. Good stuff. And then when we're integrating with respect to y, and then x in turn will go from 0 to 2, and z 0 to 6. All right, 2 more. So now we'll have dx be the most inside. So we'll go from, that would go from 0 to root y. We have our x times y times z. And then let's do dx, dz, dy. And so with dx, dz, dy, the next one would go from 0 to 6. And then y would go from 0 to 4, as we discussed earlier. And then the last way we would do it, we can set it up is, let's see, x times y times z, and then dx, dy, dz. So this would again be 0 to root y. Then we would have 0 to 4, and then 0 to 6. So these are all different ways that we can, that are the 6 different ways that we could set this triple integral up. All right, and actually I'm really sorry, this is one of the, I chose to do a different applications, so we're actually not finding the center of mass in moments of inertia, but that's okay. You've got your triple integrals set up. All right, so I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe and tell all your friends. Bye.